Hi, everyone. I'm Junyi from Peking University. Today, I will talk about our work, BurstCBS, an I/O scheduling system that allows burst while limiting tenant interference. This is a joint work with Qian and Ennan from Alibaba Cloud, Xuanzhe and Xin from Peking University. Cloud block storage is the key building block for cloud computing. At public clouds like Alibaba and Azure, cloud block storage is disaggregated into 3 layers. At the compute layer, a storage agent abstracts the backend storage as virtual disks for user VMs. The position cluster provides a generalized distributed storage for different services, including block storage, object storage, and file storage. And block storage specific logic, such as segment management, is built into the partitioning layer. This 3-layer architecture allows fast failover and flexible resource provisioning compared to local disks. Yet we always strive to provide more elasticity, not only when you provision your VMs and disks, but also at runtime. Burstable VM becomes attractive these days. In addition to the guaranteed resource provisioning like normal VMs, it allows you to use additional vCPUs when needed. If you have a workload that has many unpredictable CPU usage spikes, Burstable VM is a great choice. There are also a lot of I/O-bound tasks which share a similar pattern. Therefore, many cloud providers, including us, also provide burstable virtual disks which can burst to a higher IOPS and bandwidth than your provisioning. So before we move on to burstable IOPS and bandwidth support, let's first look at how the maximum provisionable IOPS and bandwidth is determined at Alibaba Cloud. We take each individual component and measure them with various workloads. We derive the maximum IOPS and BPS from the results and make sure we don't provision IOPS and BPS beyond that. Then it comes to next question. Apparently, saturating burst requires extra resources. Do you have enough IOPS and BPS at each layer to support burstable virtual disks? Or do we need to provision more resources, or we already have those spare resources there? Starting from the position layer and partitioning layer, our first insight is, although 78% disk capacity is used, IOPS and BPS utilization is extremely low, and the CDFs are almost vertical lines. This is because our data placement strategy balances the load at both layers, so we conclude that we have plenty of resources available at the backend layers. In contrast, IOPS and BPS usage on the compute nodes is very diverse. Over 80% of the tenants use only less than 50% of their provisioned IOPS or BPS. This is kind of expected because resource over-provisioning by cloud users is very common. But we also observe the long tail on the burst. So can we just let burst tenants use those idle resources? This is a 30-minute trace when some tenants were bursting. Although the resource utilization of the victims is extremely low, we still observe unacceptable high average latency on them. How did that happen? Storage virtualization is handled by XDPU on the compute node to save powerful host CPUs for VM usage. XDPU is an SoC which has WinP CPU cores, NIC, and FPGA. We take NVMe write as an example to explain how it works. After NVMe command arrives at FPGA, FPGA starts copying data assisted by DMA engine. At the same time, a control thread running on a WinP CPU pulls I/O metadata. And when it finishes header encapsulation, it notifies the data plan. When both header and data are ready, the packets are dispatched to the backend. In this workflow, each component on XDPU can become congested. The major source of congestion comes from load imbalance. In this example, IOs from CPU 1.1 and 2.2 are both mapped to control thread 1. When CPU 1.1 starts bursting, IOs from CPU 2.2 are impacted. And based on our observation, load among these CPUs can be very skewed. Even without load imbalance, interference also happens when multiple tenants competing for resources. On the left side, we increase the I/O parallelism of a enabled tenant. Average latency quickly increases after a certain point. On the right side, we have 2 generations of virtual disks running on the same compute node. We keep increasing the I/O parallelism of product B disk while keeping product A disk parallelism unchanged. Apparently, product B is at a disadvantage when competing with product A. With these findings, to provide burst capability with interference minimized, we need an I/O scheduling system on X CPU to keep load balanced among threads and also allocate resources for tenants within a thread. Our system BurstCBS consists of 3 parts: high-performance queue scaling for efficient load balancing, and burstable I/O scheduler with vectorized I/O cost estimator for intra-thread scheduling. On XDPU, FPGA acts as a switch. With limited FPGA resource, XDPU only has 1 egress queue per ingress queue. When a vCPU bursts, load imbalance happens. A common approach to mitigate load imbalance is work stealing. However, in our current setup, it incurs about 35% throughput loss. To achieve load balancing at line rate, we added more FPGA resource for our newest version of XDPU to support more egress queues per ingress queue. So IOs from 1 egress queue can be evenly distributed to the thread at line rate. However, this approach creates pressure on memory management. The main goal of memory management is to avoid memory allocation on the critical path. So we used to keep a shared memory pool at initialization. When we attempt to support millions of IOPS on a single node, we discover that prefilling VM, virtual disk, or IOQ related information also impacts the overall performance. Therefore, we separate the shared pool into IOQ dedicated pools, so we can prefill buffers only once. With more queues added, we have fewer memory buffers per queue, which limits number of parallel IOs we can support. To combine the benefits of both solutions, we adopt a 2-tier memory pool. Prefilling only happens when buffers are moved from the global pool to a per queue pool. With load imbalance addressed, we move on to scheduling inside a thread. There are 2 existing approaches at Alibaba. BurstCBS gives each tenant a fixed amount of resource per loop. If a tenant does not use its resource allocation, then it's wasted. WideCBS instead allows burst by allowing using resources of other tenants. The problem arises when low usage tenants and burst tenants coexist. Because the I/O loop is quickly occupied by burst tenants, IOs from low usage tenants always have to wait for at least 1 loop to get processed. To support burst while protecting performance of base level tenants, we propose Burstable I/O scheduler. Burstable I/O scheduler predicts usage of next window based on historical stats. If a tenant uses less resource than its base level provisioning, we try to reduce its allocation. The idle resources can then be allocated to burst tenants. We repeat it for every scheduling window. To protect base level tenants, they are allowed to steal resources from burst tenants. And we keep a shared resource pool for base level tenants to fall back to. We intentionally choose a heuristic-based approach so that it only takes linear time to run each scheduling cycle and constant time to process an I/O. This is important as WinP CPU cores of XDPU only have limited processing power. A complex algorithm results in both high tail latency and lower peak throughput compute node. But how do we describe how much resource an I/O consumes on XDPU? For SSD cost estimation, as vendors provide very limited information, existing work adopts a scalar cost model with linear estimation. However, XDPU and its software are more transparent to us. We identify that different I/O patterns have very different bottlenecks. If we use the most consumed resource as a cost, there will be a significant amount of wasted resources. But if we describe cost as a vector of different resources, the overall resource utilization can be improved without causing congestion. We conducted a comprehensive evaluation to show BurstCBS achieves the desired benefits. For all of the experiments, we use a compute node which has the newest version of XDPU. We compare with both base CBS and wild CBS on different types of I/O patterns. BurstCBS is able to distribute I/Os from multiple control threads with near linear scaling, and our load balancer is nearly equivalent to dispatching the same amount of I/Os from each vCPU. With BurstCBS, tenant interference is also significantly reduced. When there is a burst tenant in the background, BurstCBS is able to reduce average latency by up to 85% and is very close to base CBS. And at what cost do we achieve the performance isolation? The maximum burst capability only drops by 5 to 8%, which is primarily due to the shared resource pool we reserve. We also verify that application actually benefits from BurstCBS. We evaluated both open source database systems, MySQL and RocksDB, and our management database service, RDS. And we observed latency reduction during burst for both cases. We also reproduced amplified production trace and successfully reduced average SQL query latency from up to 47 milliseconds to less than 10 milliseconds during a 30 minutes period. For more detail, please refer to our paper. To summarize, BurstCBS is an I/O scaling system that supports bursts and keeps performance interference limited with low overheads. It employs high-performance queue scaling for efficient load balancing, burstable I/O scheduler with vectorized I/O cost estimator for intra-thread scheduling. It provides up to 85% average latency reduction during bursts. Thanks for listening, and I'm ready to take questions.